We have already seen this problem when we discussed how to formulate a reliability problem. This involves design of an intersection from transportation engineering. So we have to make sure that the required side distance is less than the supplied side distance, but there are random variables involved. So let's solve this problem with some typical numerical values. So on the top left you see the limit state, which is m, the s supplied minus s required. All the random variables are defined and all the other constants are defined. And it's also stated that the supplied side distance is known to be deterministically 140 meters. So suppose only t, the time, the perception reaction time, is the only random variable, and all other parameters are fixed non-random at their design values. So we can solve this problem under various assumptions that this t, random variable t, is normal or log normal or viable, and it would be a simple exercise. You have solved these problems already several times. So if you want to work through them, please pause the video. Otherwise, let me present the answers. When we fix the non-random parameters at their design values, we get a limit state failure as t greater than 2.52. So here failure is written in an inverse form. Typically we have g less than 0, but here t is greater than 2.52. So you can think of it as 2.52 minus t would be our limit state function. Anyway, so when t is normal, we can solve it, and the answer comes to something like 4.3%. When t is log normal, we can solve it, and the answer is a little different. When t is viable, we can also solve it. The answer is again smaller. So clearly, and we know by now, that the distribution of the random variables can significantly affect the answer in terms of PF or reliability. But we have a more interesting question here, is that what if t is not the only random variable, which is what we should expect, and what if VA, the initial speed, and FA, the friction coefficient, they're also random variables, and we can define their properties either from data or from the literature or from some reasonable assumptions. In either case, how will we estimate the collision probability? It's not a simple CDF calculation anymore. There are 3 random variables involved, and there is no way that we can combine all of them into a nice analytical closed form answer. So what we are hinting at here is that there are situations, and which are more common than the otherwise, is that we have to resort to approximations. We have to come up with estimation techniques for failure probability where an exact solution is not readily available. So we need approximations, and we are going to present them very soon. But let's go through one more example.